Oh, today is October the 30th. And very soon we are going to have our we're going to go spring forward, fall back, right? Very soon. When does it happen? Must be next week, maybe. Uh, daylight saving. When daylight saving ends, right? Daylight savings. Yeah, November 5th. Okay. November 5th is going to be about, this coming Sunday. Okay, so here you go. We are writing here. I asked you to read the remaining of uniform circular motion in that not read, but to look at the recordings of uniform circular motion with examples. Syllabi, here you go. I'm going to start sharing my screen as well. Go get my notes here, 2023 notes. Insert page break. Today, October the 30th, 2023. That's going to be a Monday today. And some news here. Let's see, one, right? Daylight savings ends. Daylight savings ends on November 05. So starting next Monday, we're going to have, we have to adjust our clocks. That's one thing. Last time, I asked you to review the recordings. The recordings on uniform circular motion with examples, right? So I consider that chapter 5 was done, considered chapter 5 was done. And here you go, let me erase that. Here you go. That should be when I just, today's Monday, we're writing here. And that should be work, the idea of work. And rotational motion should be chapter 8. And let's not forget, Wednesday is our exam. Wednesday is our exam. Chapters 1, 3, 4, lab 2. And reminding you, right? Next meeting is exam 2. What else we need to know? I corrected reports for labs 1 and 2, and I want to go through that, how you're going to consult your corrected report. Okay, I correct lab reports for lab 1 and 2. Here you go. A, already uploaded the correction to your group folder. And I'm going to walk you through A. I am going to walk you through how to visualize your corrected report. Okay. I do that every semester for physics 6. Because I do something different, I do it different, and because I do that every semester, already have everything typed up before. Let's take a look. Lab report, fall. Let's see. Lecture notes. Here's my lecture notes from last semester, which, by the way, is posted, right? Let's make sure it's posted. Okay. Both the notes of last semester and this semester. LAHC, login, Canvas, sign in. And here is my, let's see, links to video. Yeah, lab notes. Why did I put lab notes here? Interesting. 2022, but it looks like it's just lab notes. Can't be only lab notes. Let's take a look. Yeah, it looks like it's just lab notes. Yeah. Okay, so let me upload the last year's notes. So you have that as a backup. Those are the notes for the fall 2023 and files. Here you go, right in here. Yeah, okay, so here you go. If you go in my hard drive, see that? I have the lecture notes for the fall 2022. And I will upload that as well. And we can go back. Links, lectures and lab notes. We are going to get the file here. Lecture notes right here, add item. Okay, and I will move it up here. Let's see when everything is updated. Lab number 4, Wednesday, right? 25th, yeah. My notes are updated. Let's take a look at the links to the videos. Yeah, the video is also updated, the latest one. Oh, by the way, it's an older video, right? From last year's. Since I didn't cover on the spot uniform circular motion, I decided just to upload the video just for you to make things easier for you. Okay, home. And here are the notes. Let's see. Notes, P06 2022. Let's take a look at this one, lab notes. Enable editing. Let's see. Corrected. Okay, lab 1 was correct. Okay, good. That's what I want. So those are the instructions on how to access. I'm just going to copy and paste in the updated notes. Okay, corrected reports. I'm going to walk you through how to visualize your corrected reports. Okay, step-by-step instructions on how to see your grade, your report grade, your lab report grade. Okay, so here you go. 1. What a funny thing. Let's see here. Yeah. Step by step. Let's see. Okay, good. Let's correct it and upload to your group folder. Okay. Effort for level was correct and uploaded. Okay, go to your group folder. That's the first step. B, right? Identify a .html file in your group folder. For instance, group number 1. For group number 1, this file is P06L01G01HTM. Okay, and I'm gonna show that to you for you there in the Google Drive as well. Google Drive. More students coming. 2023 fall folder. Okay, so here you go. HTML, this one here for for lab number 1. Lab number 1, group number 1. Identify this file. That's the first step. What's next? More students coming in. See? Download this file to your hard drive. Okay? Then download the folder associated with this HTML file. Okay, so here you go. We have the HTML file, but we also have the folder associated with the HTML file. It has the same name with the exception of the files here. You need to download both documents. I need you to do that right now, okay? Go to your group folder and do that right now. And like I said, I'm gonna keep it, I'm gonna leave these instructions in my notes. So here you go. To download, you can download them separately or you can download them simultaneously. It's up to you, okay? You download them separately. You go one by one, download. It usually is downloaded to the download file. Here you go. Because of the HTML file, it shows here as a Google browser, right? So it's downloaded. Then we have to download, just download the file is not enough. You gotta download the folder as well. So I'm going to download the folder. Here you go, download it. It's gonna show up in my, first it's gonna be compressed. It's zipping. First it's gonna be compressed, it's being zipped, and then it's going to be downloaded. And it's gonna be downloaded to the same spot. Here you go, the same folder, right? Download folder right in here, zipped. And notice that we have just one, that folder that was in your group folder in Google Drive. So what you have to do, after downloading, then download the folder associated with this HTML file. For group one, this folder is entitled, right? The folder and file you downloaded usually end up in your download file of your computer. Okay. Go to your download folder in your computer. Okay, the HTML file is already in the proper format. It's not zipped. Okay, so you don't have to worry about that. It's its proper format. So you don't have to do anything for now. So you don't have to do anything. What is it? Yet. However, the folder you downloaded is zipped, and you must unzip it. Okay, so here you go. To unzip the folder, double-click the zipped folder, copy the contents, and paste in the same folder where your HTML file is located. I'm gonna do that. Right in here, right? I gotta go inside this folder. Okay, right in here, the zipped folder. Click the folder that you downloaded, copy it, and then paste it in the same folder where this file is located. You gotta make sure that both the folder and file, why I didn't do it? Let's see. Let's try it again. Doesn't look like a copy. Copy it, huh? Yeah, let's see, it's pasted now. Okay, now it's pasted. Now we're going to work with those two files, or with those two documents. This file and this folder. They must be exactly in the same folder. Don't drag this one to inside. Don't drag it. Are you all following? Okay, and going back here to unzip the folder, double-click the zip folder, copy the contents, and paste in the same folder where your HTML file is located. J. Okay, so we're done that now. Double-click the HTML file. Okay, double-click the HTML file. And then once you double-click the HTML file, you will be able to see the contents right in here, okay? That's what you should see for, if you have too many mistakes, you're gonna have all those colored. And here is the table with your mistakes and your grade, your final grade is here. Okay? So let's make sure that everybody got that. That's the step-by-step procedure. Erase that. Good. Okay, and what I'm gonna do here, let me copy that. Let's see if I can put it here. Look. Yeah, like that. Like that. Step-by-step procedure. That's the way I have been doing for several years. It has been working very well. I have no reason to change. Students have been able to look at the correction, at their correction. All those years. And I did that for lab number 2 or as well, right? You gotta do the same step for lab number 2, for the report of lab number 2. 9/11. Let's take a look at the. Any questions? Your grade should be at the bottom here or at the top as well. I kept the grade at the top as well, okay? Let's see here, right here as well, grade. Okay. So the grade is both at the top and bottom. Check your grade, let me know if you have any problems. And the number of points that I am subtracting is right here in this column, okay? What do I do? You know, I document what is incorrect, right? If you miss the units, you know, I'm gonna count how many units you used, you missed, and I take out like 2.5 points from each unit, and then that's how many points I will take out. Then I determine how many significant figures you're missing, right? I'm taking 0.8 points for each significant missing significant figures. How many significant figures you added, okay, and so on. R squared, CL, slope, and then I go through the optimization of the graph, the labels of the graph, number of the graph, and so on, okay? So the sum that you see here is how many points I'm going to subtract from your grade, from your 100% grade. So in this case, this group got 100 minus 48.6. Okay. Let's take a look here. Attendance, lecture. Oops. Okay, yeah, that's right. This is the 30th. Sky, are you there?
Here.
Okay, then just we'll see lab 3 corrections before the exam. Well, I want you to read one. I want you to take a look at the mistakes that you made in lab 1 and 2. Okay, first, and once you go through, you know, once you go through your mistakes of lab 1 and 2, I'll give you, you know, you might want to review your lab 3. Okay, you might want to review your lab 3. I'll give you a little bit more of time for you to you know, to review your lab 3. Make sure you don't make the same mistakes that you made on lab 1, okay? So what I want to do, that's a very good question, okay? So what are we going to do? We have an exam right on Wednesday, right? So let's do the following. Okay. Okay. Go through the mistakes you made in lab 1 and go through the mistakes you made in the reports of lab 1 and 2. Okay. And use these mistakes to ensure your lab 3 and 4, the report for lab 3 and 4. Ensure the reports for lab 3 and 4 are correct, okay? So I'm going to do the following. I will give you until next week, until Wednesday, 8th, until November 8th, Wednesday, to resubmit lab 3, right? To resubmit lab 3. Okay. Graph numbers. Which group are you, Ridwan? Group 3, right? Group 2, okay. So let's see, let me finish here. I will give you until to resubmit lab 3. Don't forget that the report for lab 4 is also due on November 08th, okay? So let's see what's going on here with your correction. Can I display your correction here for everybody to see, Ridwan? Go for it. Okay, so let's see what's going on there. 23, group number 2, right? Spreadsheets, corrected. Here you go. Let's take a look what's going on here. Okay, that's your. Okay, so what you missed was the CL. Okay. Don't you? That's okay. The graph don't display there. That's true. But when let's see what you missed. Okay, the only thing that you missed here was the optimization of the graph. Okay, you missed the CL. Yeah, you did miss the CL and the graph optimization. The graph optimization I cannot, for some reason, Excel doesn't copy it here into this file. But I saw your graph and noticed that there were blank areas there that were not necessary. They shouldn't be there. Okay, that's why I'm taking out like 7 points from the graph. Okay, what are you referring to? That's right. The graphs they don't display in the HTML. You're right. You're right. Excel doesn't display the graphs in it. Yeah, Excel doesn't display the graphs there. But if you want to know what you missed in that graph, just come during my office hours and I'll show you from your spreadsheet. The PNG that are in our folder show the graphs and they don't match up what is in the original PNG. Let's see. Well, I am keep in mind that I correct the graphs that are in the spreadsheet, okay? I correct the graphs that are in the spreadsheet. Let me take a look here. And either in the spreadsheet or in the hard copy or in the Word document. It's better for me if you put all the graphs there in the Excel spreadsheet. Let me see, PNG. I don't see the PNG files here in your group folder. In the files folder. Are you talking about this one here, the file folder? Okay, let's see here. Image, interesting, right? So they save it. Yeah, that's right. I didn't look at that. I look at what is in your spreadsheet. Okay, so if I go to your spreadsheet, it's not the one I look at for correction. Let me open your, here you go. Here's your, see? Yeah, that's right. It doesn't match up. Okay, so you don't have to worry. But the one I look at is this one that's here inside your Excel. Okay, see that? That's the one that I grade. Okay, that's the one that I grade. Okay, do you see this big blank area here? Okay, I took out points because you didn't adjust the the numbers. Okay, this one is okay. You got 100%. Nothing to subtract. But in those two graphs, okay, there was those two. Oh yeah, I did. Oh yes, I did. Yes, I did. You have to, remember, double click here. Okay, when you double click here, you adjust minimum and maximum, right? I did that in the classroom. I showed that to everybody. You can review the videos. To stop your graph right in here, you had to put 6, right? If you put 6, now you optimize your graph space. Yes, I did that. I did show to you all in the classroom. You can even check, review the recordings. And lab 1, remember what I did in lab 1, right? In lab 1, I asked you to work on lab 1, to upload lab 1, and then I went through everybody's lab 1 so everybody could get a good grade for lab 1. Okay, and I did that, the adjustment as well in the axis. Not only in lab 1, but also at the beginning of the semester when we were working on the graphs, on the spreadsheet graphs. Yeah, I did that. Okay. So let's take a look here at our, let's see, Sky, are you there? Sky is here, right?
Hello?
Yeah.
I'm here.
Do you have any questions about the correction, the HTML file, Sky?
No, I was able to see my grades.
Okay, good. So you were able to open everything. That's good. And Tessa, were you able to see everything?
Yeah, I was able to see all the grades and everything in the corrections.
Okay. Any questions?
No, I understand.
Okay. Destiny is not here, right? And next one is Gael. Gael disappeared. And next is Ridwan. Ridwan is definitely here. Okay. Were you were able to open the files, right, Ridwan? I see. Ashley, yeah, yeah. Okay, good. Ashley is not here. Norberto Lopez. Norberto is not here. Annabelle. Hi, Annabelle. Are you there? Okay, I don't hear from Annabelle. I'm gonna put here a little star. Vanessa, are you there?
Yes, I'm here.
Okay, do you have any, were you able to open the files?
Yeah, I was able to get it open.
Okay, any questions?
No, everything. Well, other than that, I wanted to ask about a graph, but you said we can ask about that during office hours, so
Yeah.
get that.
Okay, good. Catherine. Catherine is here. No. Next is Camden. Are you there, Camden?
Yes, I'm here.
Okay. Were you able to open the file, HTML file?
Yes.
Okay, good. Victoria Preciado. Are you there, Victoria? No. Alexis Richardson. I don't see Alexis. Marco Sanchez. Okay, here. Okay, were you able to open the file, Marco? Okay, good. So we have 7 students. We're in good shape. Okay, so we're done with this part. So what I want to do, start with the concept. What do you mean by sig figs added? Well, suppose that the number has only 3 sig figs, right? Suppose it's supposed to have only 3 sig figs. Sometimes the students, instead of displaying 3 sig figs, they display 4, okay, or display 5. That's what added sig figs mean, okay? Whenever you display more significant figures than the the number is supposed to have. Okay, and then you can do the opposite too, right? You can display, less significant figures than you're supposed to display, right? Starts the concept of work. And let's take a look here at our book as well. I leave this. The Wiley course resources. Launch. Chapter work and end. Oh, wait a minute. Oh yeah, there you go. That's the, we have banked curve. Oh, we also have a satellite in circular orbit, vertical circular motion. So what I want you to review, not for this coming exam, right? But for the third exam, let me document what you need to know for this chapter. Let's look. Okay. Material for chapter 5, 5.1, UCM, uniform circular motion. 5.2, centripetal acceleration. Don't forget, every time that you have an acceleration, you are also going to have a force, centripetal force, every time, right? According to Newton's second law of motion, if the acceleration is different of zero, it means that the net force is also going to be different of zero. And then we have those problems of banked curves, satellites in circular orbit, using the force of gravity, apparent weightless, which is weightlessness and artificial gravity. That's a very interesting effect. In the case of artificial gravity, there are lots of movies out there that do a very good job, not just a very good job on artificial gravity, but they also do a very good job on apparent weightlessness. So in artificial gravity, you should watch 2001. Definitely 2001, the movie. It's a classic. It's a classic, not just a science fiction classic, but it's a classic, a cinematographic classic. Everybody refers to this movie. And it was filmed back in the 1960s. Okay? Stanley Kubrick directed that. Everybody, refers to this movie whenever they want to do science fiction movies. But it's not just science fiction movies. It's also, the movie is so important that it's a reference for any movie at all, any movie altogether. The other one, another concept, the concept of apparently weightlessness, was very nicely dramatized in the movie Inception, right? Leonardo DiCaprio. I liked how they did those apparent weightlessness scenes, not just apparent weightlessness scenes, but the scenes in which they accelerated the elevator as well by putting some charges in the elevator in case that you have watched the movie. It's really, really impressive what the work that they did in Inception. I really like that movie. And then we have vertical circular motion. Okay. like I said, some movies do a very good job with their physics. And it becomes not just a matter of entertainment, but also becomes what they display there. The movie becomes a matter of education as well. So those are all the materials that you gotta keep in mind. Okay. And what we want to do, but I want to start next. Start chapter 6. Work. But before I start in chapter 6, I was playing a little bit. I don't know if you folks had time to do that, okay? But this weekend, I was playing for the first time. It's a little bit off topic, okay? It's not physics, but I think it's very important because we should be using that all the time. What am I talking about? I'm talking about artificial intelligence, right? Intelligence. My first this weekend was my first contact with, this weekend was my first contact with ChatGPT. It was rather impressive how how ChatGPT works. Have you ever done that? Have you ever worked with anybody here has ever worked with this ChatGPT? I want to hear from you. Not just ChatGPT, but there is other types of artificial intelligence software that also generate pictures, right? ChatGPT is very good. It's very good for generating text. I like it. It's pretty impressive. Save on a bunch of work. Anybody here has ever, I want to hear from you folks. Let me go one by one. Have you ever used ChatGPT before, Sky? ChatGPT is in the news, right, all the time. Looks like Sky is not here. It's not.
Could you repeat the question?
Yeah, have you ever used ChatGPT?
Yes.
Oh, you have? Oh, cool. Yeah, what we're doing? Were you generating text? Exactly what we're doing when you're using ChatGPT?
I was brainstorming for a paper I was writing with it.
Oh, I see. So you're talking to ChatGPT and asking him to help you with your paper, right?
Yes.
Okay, yeah, it's very impressive, very impressive too, right? I really, yeah, I was really impressed with that. And thank you for sharing that with me, Sky. And Tessa, have you ever used ChatGPT?
I've never used it.
Never?
No, I haven't tried to.
Haven't tried? Okay, so let me put it. ChatGPT. So Sky has, Tessa hasn't. Okay. So you might want to, take a look at that. It doesn't take much effort to work with ChatGPT, It doesn't take much effort unless you're writing a book, let's say. If you're writing a book, then you have to keep on interacting back and forth with ChatGPT to help you make the text better and better, right? So maybe I should feed all those notes of mine to ChatGPT and see what he is going to output it. Ridwan, have you ever used ChatGPT before? No? Yeah, haven't had a need, but I have seen my friends use it. Okay, cool. Yeah. Yeah, it's a very, I'm impressed with that tool. Yeah, has been around for some time already, right? And I would say I would encourage you all folks to use this, just like a new tool that's in the block that's available, right? And some instructors are against students using ChatGPT. I think it's a huge mistake. I think that instructors should encourage you all to use the tools that are available out there. It's like preventing a student to use ChatGPT is like me preventing you from using Excel. Okay, it's like that, we're doing graphs all the time, and I come to you and say, you're not going to use Excel to plot the graphs. I'm going to plot the graphs all by hand. Back in my times, we used to do that. Oh man, it was a really pain to do that by hand. And the professor wanted us to do a very nice, clean graph that would take hours to generate by hand, right? So let's see. Annabelle, are you there? Giving opportunity for Annabelle to review herself. Hello, Annabelle. Okay, no answer from Annabelle. Next, Vanessa. Vanessa Mena.
No, I haven't used it before.
You haven't? Okay.
No.
Okay, nice to hear. So Catherine is not here, right? And Camden, have you used
Did you call my name?
Huh?
Did you call my name?
Oh yeah, I did. Yeah, just my question is, have you used Chat GPT before, Annabelle?
Yes.
Oh, you have. Okay, good. So can you tell me what we're using that for?
Oh, I meant no. I'm so sorry. That was a no.
No, there was a no. Okay. Okay, so let's go for Camden now. Camden, have you used Chat GPT before? No answer from Camden. Okay, I'm gonna put a star here. Then finally, Marco. Have you used Chat GPT before, Marco? Yes. Oh, okay, cool. Can you elaborate a little bit more? What were you doing with it? What you're trying to, accomplish, and troubleshooting some code? Really? It does that too? It's not just regular text, but also they help you troubleshoot code. Wow, I didn't know that. Yeah. Okay, I didn't try this feature, So Chat GPT, right? If you have never used Chat GPT, let's take a look here. Chat GPT. Open AI. Okay, I have, let's see, how to draw. See, I was asking, let me see, not this one here. Recovery not possible, song lyrics. Okay, so here you go. Here is one of interactions I had this week with Chat GTP, right? So there's this song, Alan Parsons Project song, that's called Day After Day, and tells a very nice story, this whole song, right? And so what I did, I copy and pasted the lyrics of the song in ChatGPT and asked him to generate a text, a story based on these lyrics, right? Okay, so look, I didn't say anything to ChatGPT, right? I just copy and pasted, I didn't say anything. And then what ChatGPT replied to me? This lyrics appears to be from a song. Okay, he already knew it's a song even though I didn't tell him. But you haven't specified the artist or the song's title. Can I help you with something specific related to these lyrics, like an explanation, interpretation, or any other questions you may have about them? Oh, create a story out of this music, out of these lyrics, right? I asked him, okay, certainly. And then he goes and he even give a title, right? To the lyrics of the song. Okay, certainly I can create a story inspired by the lyrics you provided. And then this guy just do just like that, right? If I were to create a story like this one that ChatGPT created, and let's see, 1 paragraph, 2 paragraph, 3, 4, 5, 6, 7 paragraphs. Let's see what was the length of that story that he created based on the song, right? Let's see, if I were to create something like that out of my head and inspired by what the song, the lyric of the song put, right? This is a one page text. A one page text is something that takes like half to 1 hour to generate, because I have to go back and forth, improve here and there. But then ChatGPT did that, in 15 seconds, right? Less than 1 minute. Okay. So that's really nice too. And that's the interaction I had with ChatGPT. I asked other things from ChatGPT. That's one type of AI we have out there. And there's another type of AI, AI to generate text, right? And according to Marco, right? Even computer code. Yeah, sometimes we make a mistakes on those codes, right? Right, Marco? And we cannot find a mistake on the code that we wrote. So we can have the AI to troubleshoot that for us and pinpoint exactly what is wrong, where it is wrong, okay? And how we should do that, and how we should rewrite the code. But in addition to generate text, there is also AI for generating drawings. Okay, yeah, the AI can paint that, can create illustrations as well. And there are a bunch of AI out there that can do that for you. The one I like the most, I even asked the ChatGPT what are the artificial intelligence programs that they have to create illustrations, right? So if you are an illustrator, you can do that by hand, right, on your own. But then you can also hire one of those artificial intelligence to create something like that just in the snap. And the ChatGPT, gave me some hints on type of programs that can create illustrations. Here you go. I'm going to copy and paste here. I asked ChatGPT, right? And let's see what he applied to me. Here you go. Yes, AI can be used to generate pictures and artwork. That is a reply from ChatGPT. I asked it, AI can generate pictures and artwork, right? Yeah. There are AI programs and tools like deep learning-based neural networks that have been trained on vast data sets of images and can generate visual content, including drawing, right? Artistic style transfer. That's a type of AI, generative adversarial networks, Deep Dream. Deep Dream is available there for free. I started using Deep Dream, but I didn't like Deep Dream. It doesn't do the illustrations that I specifically asked to Deep Dream. I do not know why. Okay, image to image translation and so on, right? But the one that I liked the most, I found one specifically for storyboards. Storyboards is used to illustrate the scenes of a movie, okay? They call it boards. Do you see that? All those images were generated by an artificial intelligence. This picture that you see right here was my interaction with this artificial intelligence. I asked them to draw a room with seats, okay? And he came up with this. All the other pictures that you see right in here was already in there when this is another one that I asked this artificial intelligence software to generate. Inside of an airplane with seats, okay? But the other ones was already there when I logged in. It's pretty, interesting. It's already colored. Do we have different types of illustrations. This one is like comics illustration, and you can choose what type of illustrations you use. Okay, so just a little thing that to share that with you. If if you find anything like that you enjoy, that you like, let me know. I'm looking specifically not just the text but the illustrations to create storyboards of my own classes, let's say, right? My own classes. Okay, just like my PowerPoint pictures that I share with you. So just a little aside here. Now we can start with chapter 6. P120, this one here. Okay, think about that, right? All those slides done by an artificial intelligence program, right? The quality would be much better than that. Would be done much quicker, much quickly too. And maybe I should just interface with that program, and while I'm teaching you, I ask the artificial intelligence to draw exactly what I want, right? I didn't get there yet. Maybe that's because the artificial intelligence didn't get quite there yet either, because I haven't found an AI that would do the drawings exactly the way I tell them to do. But that's the type of world we're living today, right? We can get robots to do lots of those tasks that are very time consuming for us to do. All those illustrations that you see right in here, sometimes take some time. It takes quite some time to generate them, and they don't end up quite in the way I want them to end up. But let's go here, go to the work 6 example. Friction, right? Let's get with the topic of work. Okay, he got the elevator that's accelerated. I paid an artist to do those two drawings, okay? I did pay an artist to do those two drawings several years ago, and now if I learn how to work with those artificial intelligence programs, they can do that for free for me. And the nice thing about artificial intelligence is that even though it was the artificial intelligence that generated the text in the picture, right, the illustration, the copyright of those artwork and the text is yours. Okay, it's not common. It's not public domain at all, and it doesn't belong to the ChatGPT either. You can claim as your own copyrighted material. I asked this question to ChatGPT, and that's what his answer was. So far, the artificial intelligence cannot copyright their own material, right? But whoever interacted with the artificial intelligence keeps the rights, the title to the material to the copyrighted material that was generated. Okay, that's where we want to go here. We want to start with work and energy. Okay. Energy is a concept closely related to work. And in physics, we first introduce the definition of work, and later we work out the definition of energy. Like here you go. Work, chapter 6. Work and energy. Work is a concept closely related to energy. But before defining energy, in physics, we first define the concept of work. Okay? Work is a concept that depends on a force applied to an object and the object's displacement and its displacement, okay? the object displacement. It's a mathematical definition. Keep in mind, the best way of defining work, it is a mathematical definition. Okay? Okay, so every time we talk about work, we're talking about the work, this idea of work, is specifically stated as the work of a given force or the work of a given set of forces. Okay? And we need this definition of work to elaborate on the concept of energy. Mathematically speaking, okay, but before mathematically speaking, right, we gotta make an illustration before we define work mathematically. First, we have to come up with an illustration, right? And the illustration goes just like that. Here you go, we have an x-axis, we have a y-axis, and we have an object placed right in here. We say, if we apply a force to this object, a genetic force, any force, don't forget this object already have two forces applied to it, which is the weight and the normal, right? If we apply a force to this object and the object displaces, okay? Remember, work is a concept defined in terms of a force and a displacement. We say that the work done by this force, okay, is going to be the component of the force along the displacement times the displacement. That's the mathematical definition of work, right? That's the mathematical definition. And you have to, so let's say here we have another force, right? In the horizontal direction. This force is 1 Newton. The object displaces 1 meter. Then the work done by this force is going to be 1 meter times 1 Newton. Okay? So here we go, mathematical definition of work. Of work applied, work of a given force, right? Let a force F be applied to an object. If this object displaces a distance delta x. This delta x and f sub x is the x component of the force F along the displacement, okay? Comma. We say that the work done, we define, right? The work done by this force as being let's get, here you go, my equation here. Paste it. Work done by force F is going to be F sub x times delta x. That's the mathematical definition. That's the starting point of everything in this chapter, which, by the way, you know, is going to be the full force F times the cosine of the angle that the force makes with the horizontal times delta x. Okay, here you go. That's the definition, that's the mathematical definition of work. Unit of work. We're going to do the unit of work, right? It's represented by this square bracket. And go the unit of force times the unit of distance, or the unit of displacement. This unit shows up so frequently in physics that we give it a name. We call it the joules, that's abbreviated by the letter J. Okay? Joules is also the unit of energy, like I mentioned, and we're going to elaborate it. It's 9:58 right now. What I want to do, let's take our little break now. Any questions before we move forward? Okay, so okay, I'm gonna stop sharing. We're gonna have our break. Wait a minute. Break from almost 10 a.m., right? To 10:15 a.m. Okay, and I'm going to come back here. And we have Norberto, who just arrived. Norberto Lopez, right in here. Okay, so let's go ahead and do some examples now of this concept, okay, this idea. No? So example one, right? Force of 1 Newton along the horizontal direction. That's instead of horizontal, along the x direction. Object displaces 1 meter along the x direction. Find the work done by this force, right? Solution, simple enough, right? Straightforward application of formulas. Here we have, you know, the angle between the force and the direction of displacement is 0 degrees, right? So I can put 0 here, 0 degrees. Here is going to be 1 Newton. Here is going to be 1 meter. And then we get 1 joules, 1 joule of work done. And then let's do another one. Example 2. Force of 1 Newton makes an angle of 60 degrees with the x direction. Object displaces 1 meter along the x direction. Find the work done by this force. Okay, so it'll be something like that. Okay, this angle here, theta, is 60 degrees, right? So we go 1 Newton, 60 degrees. Okay, that's 60 degrees. Oh, gosh. Is 60 degrees. Cosine of 60 degrees is half. Right? So we have half Newton, half joules. And now we're going to go with another example that's not as obvious, you know. An object displaces 1 meter along the x, along a horizontal surface. Horizontal surface. What is the work done by the weight? By the weight of this object. Okay, what's the work done by the weight of this object? So we gotta do the drawing again, because it's not this force, it's this force that we are talking about. We do know that the object is displacing 1 meter. It doesn't matter how. It doesn't matter which force is making the object displace 1 meter. It doesn't matter. All that matters is that the object has displaced 1 meter. That's it. Okay? What's the work done by this force right in here? The weight. Okay? Okay, notice that the weight makes an angle of 90 degrees with respect to the displacement. Okay, consequently, this angle here is going to be 90 degrees. It's not going to be 1 Newton, it's going to be mg. I didn't tell you what the mass is, but I don't have to tell you what the mass is. Why is that? Because the cosine of 90 degrees is going to be 0. Okay? So even if I don't tell you what's the m of the mass, of the value m of the mass of the object, you still can solve the problem numerically. And then we can move on to the next example. Example 4. An object displaced 1 meter along the horizontal surface. Along an horizontal surface. What's the work done by the normal applied to this object? Okay? The normal force we did for the weight. Now let's do that for the normal force right in here. Just like before, the normal in this case makes an angle of 90 degrees with the horizontal as well. Consequently, it's just like we had before. Is going to be, and this force here is going to be, I'm going to put it mg, okay? Here is going to be the normal force. I'll put normal, subscript normal. And I'm not even going to put mg, I'm going to put n. in a more generic way. You go. But because cosine of 90 degrees is 0, I don't have to know what's the normal, what the value of the normal is. Okay. By the same token that we can define the work done by a single force, comma, when I italicize that, we can also ask for the work done by a set of forces, okay? I can ask that too. So example 5. What's the work done by the normal, the weight, and the force F applied to this object? Okay, force F. In this case, the force F is along the X direction and is equal to 1 Newton, okay? So basically what he's asking, I am asking, right? What's the work done by the normal plus the work done by the weight plus the work done by the force F? That's what I'm asking. Because it is a horizontal surface, the work done by the normal is 0. The work done by the weight is 0. And the work done by this force F is going to be 1 Newton times 1 meter, which is equal to 1 joule. Like that. Yeah, we can ask that. So you can put like that, work done by the N, oh, no, like that. By N plus mg plus F, right? We can do like that. And what we're doing here, this is all those examples, all these examples are examples of the work done by a constant force. Okay? Constant force. What if the force is not constant? What is, oh, and by the way, there's one more example. Let me give you this other example here. What about the work done by this force of friction, right? So let's do example 6. Example 6, an object displaced along a horizontal surface. What's the work done by the force of kinetic friction? That is equal to 1 Newton. Huh? Okay. Well, just like we did before, it's going to be the force times the cosine of the angle times the displacement. And here's going to be F sub K. Notice that I use the F sub K, I didn't use F sub S. It's not a static friction because the object is displacing, right? Going back to the drawing, the force is to the right, the displacement, oh, the force is to the left, the displacement is to the right. And this angle here, look, this angle here is 180 degrees, right? So in this specific case, let's not forget, is 1 Newton. All right, told you here is 1 Newton. Oh, I told you here that's 1 meter. And here it's supposed to be 180 degrees. Right? Because it's 180 degrees, the cosine of 180 is -1, right? And now we have this case in which the work done by a given force is negative, is -1 joule. Okay? Note that if the displacement is opposite, right, to the direction of application of the force, comma, the work is going to be negative, okay? The work is going to be negative. According to the very definition of work. Okay, and let's take, that's for the case of a constant force. What if the force is not constant? What if the force, all the above applies to the case of a constant force? What if the force is not constant, but changes with displacement? Okay, let's see if I have an example here. Oh yeah, here you go. Here's an example of a force that changes as with the displacement. It's the case of the spring, the case of a spring. Okay. This force varies. It increases as the displacement increases, right? At this point here in the axis, the force that the spring applies to the object is 0. But as I start to stretch the spring or compress the spring, the force increases. Okay? In the case of in the case of a spring. For instance, in the case of the elastic force of a spring, okay? In the case of the elastic force of the spring, like that. You know, in the case of the elastic, here you go. I'm gonna even put it like that with a vector, okay? In the case of this force, we can write that down. That's gonna be x hat, sorry, x hat times minus kx, okay? Where the parameter k depends on the Oh, strengths of the spring. The harder the spring is, the larger this parameter. Ah, that's the elastic force, okay? Hooke's law, we call that the relation above is called the Hooke's law. I'm gonna put the law between quotes here. Ah. Hooke's force law. Okay. Okay, in this case, let's see if I have my drawings here. Oh yeah, here you go. In this case, the Hooke's force law is linear with the position or the displacement from origin. Okay, let's take a look again in the drawings here so you have a better idea. Here you go. We have this mass here at the origin. The spring is attached to the mass, and the spring has a constant K. The larger the K, the stiffer the spring is. The larger the K. In other words, the larger the K, the stiffer the spring is. If I stretch the spring, the vector position is to the right, the force ends up being to the left because of that negative sign that you saw in there. Okay? We have those other, if I compress the spring, there is a displacement to the left, and the force is going to be to the right. In addition to this elastic force, you're going to have the weight and the normal forces as well. The work done by this one is going to be zero. The work done by this one is going to be zero as well. But this one here, think about that. In this case, because the force is in one direction and the displacement is in the other direction, the work done by this force is going to be negative, right? With respect to the origin, the work done to move from the origin to this position. Okay, so here you go. At this point here in time, you know, what am I doing? I'm compressing the spring and releasing the mass. When the mass passes through the position of equilibrium, the force, this elastic force is going to be zero, but it's going to have some inertia, a velocity, right? And then it's going to overshoot this position. Try to look into that, try to visualize that. But let's take a look. When we plot f against x, but don't forget I'm doing here the magnitude. Okay, I'm doing here the magnitude. We're going to have a straight line just like that because it's linear with x. And the work done by this force can be thought about being, you know, F times delta X. This is delta X here. And this is the value of F, okay? And at this point along the axis, we are going to have a force F a little bit larger than this other one times this delta X as well, okay? So what are we doing here? What we're doing is very simple. We are calculating the area below this curve. That's what we're doing. We're calculating the area below this curve. So every time that you have a force that is non-uniform, the area below this graph is going to be the work done by this force. Okay, so here you go. Here's the area. Mathematically speaking, it's not easy to calculate something like that. You need integration. But if you realize that the area below this curve is going to be the work done by this force, you can at least find out what's the work done by this linear force here, just by calculating the area. It's a triangle, right? It's going to be this length of the triangle, this length of the triangle divided by 2. Okay? So calculating the work done by a non-uniform force is not trivial. It's not trivial because it involves different values of the force for different displacements. Okay? Strictly speaking, you need integral calculus to find this out. However, for the case of a linear relation between the force and the displacement from origin, it becomes easier to calculate that calculate the work done by non-uniform is not trivial because it involves different values of the force for different displacements. Strictly speaking, you need integral calculus to find this out. However, you must understand that for this case, the work will be the area below the force versus x graph. If the relation between f and x is linear, this area is going to be the area of the triangle, of a triangle, right? Of a triangle, which you know how to calculate, okay? So, for the case of the Hooke's law, the Hooke's force law, the work done by this force will be okay, it's going to be what? Work of kx, right? And I'm gonna put a magnitude here because it may be positive, as may be negative as well, right? Depends how you are taking the work done. Okay, so in this case here, the work done from 0 to x maximum, let's say. I'm gonna elaborate here. I'm gonna say that this one here is f maximum. I'm gonna call that f max. Let's say this is a given value. If this one is f maximum, this other one here is gonna be x maximum. Can you raise that? This area here is gonna be what? F maximum times x maximum divided by 2. In this specific case, it's going to be f max. Oh, doesn't like it. Okay, f max times x max divided by 2. We know that only for, for the linear case, if the force is not linear with x, then it's more difficult to calculate the amount of work. Okay? It's not linear with x, then you need differential and integral calculus, differential and integral calculus. Calculate the amount of work. Revisiting the case of a constant force, right? Revisiting the case of a constant force, the work done by this constant force between 0 and x max is going to be nothing but the area below this curve. So this interpretation of the area below the curve also applies to a constant force. Let's shrink it a little bit. Yeah, like that. F max times x max. Okay, so 10:45 right now. I think I'm missing any messages from you. C8, okay, we're good here. Let's go for a little, let's see what we covered so far in the book, from the book so far. So far. 6.1. Work done by constant force, right? Let's see. And we have, we didn't cover that yet. 6.2, not yet. 6.3, we didn't cover yet. 6.4, we didn't cover yet. 6.5 we didn't cover yet. 6.6 is non-conservative forces. Okay, we didn't cover that yet. Oh, 6.6, 6.7 is power. Okay, let me write it down, power. Here you go. 6.8. Other forms of energy. We didn't cover yet, but we covered this one here, 6.9. Work done by a variable force. So far we covered those two sections here. Okay, what's the rest? Work kinetic energy theorem, we're gonna cover. Work, and he calls it work energy. Many books call it work kinetic energy theorem. That's many books call it. Your book call it only work energy theorem. The other one is 1, 2, 3, gravitational potential energy. Conservative versus non-conservative forces. Conservation of mechanical energy. Non-conservative forces and the work kinetic energy theorem. Power, okay. What time is that now? So let's have our break again. Okay, break from 10:50 a.m. to 11:05 a.m. Any questions before we move into our break? Okay, so I'll see you in 15 minutes. Okay, I'm back here and okay, so we are going to do now that's work kinetic energy theorem 6.2. Oops, very important theorem that you have to memorize is important. Remember, you know, what we said, we mentioned before that we can calculate the work done by a single force. Okay. I also said that we can calculate the work done by a set of forces. Then, comma, there is one special set of forces. Then we have the work. Then we have the work of one special set of forces. The work of the net force. Okay? The work of the net force has a very simple relationship that we can derive here. Okay? So let's work out this work, this type of work, the work done by the net force. So let's say the work done by net force is equal to an applied force plus a force of friction plus the weight plus the normal. Maybe we may have other things there too, okay? But let's stick with those ones for now. I call that the net force. According to Newton's second law, right? Remember the net force, what the net force is all about? According to Newton's second law, this net force is going to be equal to mass times acceleration, right? But let's not forget also that there is an important relation between the velocity and the acceleration, which is the recalling we call that the Torricelli equation. Recall the Torricelli equation. Something like that. Which, by the way, can be here written as something like that. Right? All I'm doing here is to isolate A. By the way, if I multiply this guy by M, okay, I'm also going to get the net force, right? And then I'm going to do something else. Notice that I have the delta x here on the right side, right? If I pass the delta x to the other side, what I'm going to get? I'm going to get the work done by the net force. Like that. The work done by the net force. And let's see what's the importance of this relationship. Okay, I'm going to break it down. mv squared. And then we have minus mv naught squared. mv naught squared, like that. Oh, the important thing about this relation, is that the above, okay, holds true no matter what the acceleration of the particle is, okay? Whether A is constant or not, comma, the above still holds true, okay? Keep that in mind. The term on the right side, I'm gonna write that here. Okay, those terms here on the right side, half mv squared, we give them a name. The terms, the separate terms on the right side, the separate terms on the right side are given a special name. They are called the kinetic energy, or the energy due to motion. Okay, so I'm going to write it down here. Ke is equal to half the mass times velocity squared. Does it make sense that it's energy? If you look at these units here, you're going to see that the unit of energy is exactly the same as the unit of work. Okay, unit of mass times unit of velocity square. Mass here, velocity square here, right? The unit of mass is the kilogram. The unit of velocity square is meter square over second square. By the way, what you see here can also be written as per second square times meter. This unit right here, kilogram meter per second square, is the Newton. This other unit meter multiplied by Newton is going to be joules. Okay, so the kinetic energy has exactly the same unit as the work. But instead of calling it work, we call this thing a special type of energy, which is the kinetic energy. Okay, so now we have this relationship that the work done by the net force is equal to the final kinetic energy minus the initial kinetic energy. We also call that delta Ke. Like that, delta Ke. It's better to put it in parentheses, right? So it's very clear that the delta is that applied to the difference to the kinetic energy, not just delta of decay. That what section 4.6.2 is all about. We can use these relations to solve many problems out there. Okay. I'm going to give you one of the examples. Okay, so it's like that. Applies to an everyday situation that we have out there. Okay, using the work kinetic energy theorem. A car is moving a freeway with speed v. The driver then applies the brake and comes to a full stop in a distance d. What would be the new stopping distance if the car was moving at twice the speed? Okay, let's see if I can have an illustration here for you. Okay, the situation, I'll have to draw it from scratch. I'm gonna use this one here. Okay, I'm gonna use this one here instead. Okay, so we have this car. We go the distance d. Oh. delivery. Delivery, okay, D. The car is this block that you see right in here. Flat surface, I'm going to put the velocity vector just above this block. Okay, and we do not have those forces. We have another force, and that's the initial velocity of the car. And that's going to be the final velocity of the car. I'm going to put a V naught here. The final velocity is equal to 0. And instead of having this arrow, I'm going to shorten it like that, right? We do not have those forces here. The only force that we have is the force of friction. That's slowing down the car. I'm going to use this one here. So let's say you slammed in the brakes, right? The car locked the wheel. Like that, kinetic friction. Not. Here you go. I'm gonna erase that, erase that, erase that. All right. And then the car comes to a stop after a distance d. I shrink it, yeah. Like that, oops. Okay. That's the situation. That's the situation we have to draw. During the slowing down, the only force applied to the car is going to be this force of kinetic friction. You do have the weight, you have the normal as well, but the weight and the normal cancel out each other, okay? So what we can do is the following. Okay, apply, let's put here solution. But wait a minute, there's one more thing, right? We have the situation, and then we have the second situation. The second situation in which the initial velocity, the new, I'm gonna put it, the new initial velocity is going to be twice V naught. Twice V naught. Like that. And the question is, what's going to be the new stopping distance? Okay, what's going to be the new stopping distance if we double the initial velocity? In either case, we're going to have the same force here being applied. Okay, same car, same braking sets. The only difference is going to be the velocity that changes. Switch back and forth. Here goes. Switch, switch. Twice the velocity. Is that going to be twice the distance? Right? That's what you have to ask yourself. There is a way to solve this problem using the work kinetic energy theorem. And I'm going to do that right now. Solution. Okay, here you go. First case. That's the first case. final kinetic energy is going to be 0 because the car came to a stop. Initial kinetic energy is going to be half of mv squared. Okay? The work done by the net force, which by the way equal to the work done by the frictional force, is going to be negative. I'm going to emphasize that's negative here. This negative sign. Let's put that less than 0. The second case. Second case. Second case, I'm going to call it W prime. Okay, W prime. The only force acting on the object is going to be the force of kinetic friction, which, by the way, is equal to the previous force of kinetic friction. But now we have a different initial kinetic energy. The final kinetic energy is still going to be 0, right? That's why I have 0 here. The final velocity is going to be by, wait a minute. The initial velocity, not final velocity, sorry. Let's see, the notation here. Oh, here you go. That should be V naught. Oh, no. Yeah, the notation here. Okay, the notation here is unfortunate. Yeah, it's like that. Initial velocity V naught. Car is moving. Okay. V naught. So I call V naught equal to V, right? That's what I did here. That's why I kept the V. That's why I kept V. And I'm going to emphasize that this V prime square is the initial velocity as well. All right? Which, by the way, is twice V. Right? Which, by the way, is twice V. I'm going to go one next step. Remember that because the V is twice the other velocity, we end up squaring the 2 as well, which turns out to be V squared. It's still less than 0, but it's a different quantity. When I divide 4 by 2, I get 2. Okay. What else? Now we go back to our definition of work. I'm going to put it here. Assume, okay, well, it's important that I write it down here. Assume that the force of kinetic friction is uniform and equal in both cases. Okay? Now, recall that the work done by the net force is also given by minus the force of kinetic friction times the distance. And the work done by the other case, prime, is still the force of kinetic friction, but it's going to be a d prime. You know, something has to give in. Because the velocity is larger, you know, if f sub k is going to be the same, then the distance must be different. But then we go ahead, recall, right? That this guy here is this guy here, right? Let's put that here. Oops. Put it here. And recall that this one here is equal to this one here. Right? And then what do we do next? What do we do next? You know, we divided this equation by this equation here to try to find out what the d prime is. That's one way of doing that. Another way of doing that would be to write down f sub k in terms of what in terms of d. Okay, let's do the second way. You know, we have these two set. We have this set of two equations, and we want to find d prime in terms of d. There are two ways of doing that. There are two ways of doing, at least, right? Doing that. One, you can divide one equation by the other, one equation by the other, or two, you can solve for f sub k in one of the equations, and plug it into the other, okay? Let's do the first one. Okay, so here you go. One way of doing that would be to divide one equation by the other, right in here. Okay, negative. I'm gonna put that. This one right in here. I don't need this one anymore, right? I don't need that either. What's gonna happen? What can I do to simplify that, right? I'm gonna work out the right side first. mv squared, see that? Cancels out. The negative sign here also cancels out. And we end up with, on the right side, we end up with 1/4, 1/4. Like that. What about this left side here? Okay, we can do something similar, right? The left side, you know, the negative sign can cancel out. Not just the negative cancel out, but also f sub k, because it's the same, they're the same values. And we end up with this relationship. This guy here, which is already here, this ratio here, equal to this other ratio here. And we're done, we're almost done. We wanna find out d prime in terms of d, and then what happens? D prime is equal to 4 times d. Okay? So if you double your speed in the freeway, comma, you quadruple your stopping distance. Okay? Just because of that square term that we saw right in here. See that? Because we doubled our speed, since we have a square term here, we end up quadrupling our stopping distance. Okay? your stopping distance. So that's one nice example that you can keep in mind. And okay, we are done with this section. Here you go. I'm gonna keep on copying and pasting that so I can keep track where we are in the book. All right, we did that. And I'm gonna do this one here. I'm gonna do this one here now. Before talking about gravitational potential energy, we have to talk about conservative versus non-conservative forces. Okay? So let's talk about conservative and non-conservative forces. Okay, there are contact forces and non-contact forces. This is one way of classifying forces. But then there is another way of classifying forces by telling them whether they're conservative or non-conservative, okay? The second way of classifying forces. Now, what do I mean by conservative and non-conservative forces, okay? Definition. A conservative force is a force that its work does not depend on the path taken by an object. Okay? That's the definition of conservative forces. Contact forces and non-contact forces is rather obvious, right? The name tells you right away what does it mean being a contact force and non-contact force. But a conservative force is a concept that's a little bit more difficult to visualize. Not so obvious, right? The name doesn't tell right away what it means, but that's what it exactly means. And I'm going to illustrate what the difference between conservative and non-conservative forces. Let me see here. Oh yeah, right in here. Okay. I like this drawing. And then we can do, let's see if I have another one that I can show to you. Yeah, that's all. Yeah, there is another one that I'll have to do it from scratch that I like to show my students. But the conservative force is the following. Okay, suppose we have an object, and I'm going to start from scratch. Play the movie, right? Play the movie here. I'm going to erase everything. Start with X, Y, and Y axis. And then we place our object at the initial position. We have this object here at this initial position. And by the way, this initial position is denoted by this initial vector position R0. And then, let's say, it's not a net force, it's like a force. Let's say that we have a force being applied, a generic force being applied to this object. It's not a net force. It's any type of force. Okay, don't put net force here. 1, 2, 3. Force. And what else? This object is moving from one point to another point. That's the path of the object. Okay, that's the path of the object. And it ends up here at this other position. And then we have this other force. Here we go. Okay. Okay. So let's say, the work done by this force from this point, and by the way, we have to put one more thing here, right? I'm gonna put this object there. Something else is missing here. And this something else is the final vector position. Right in here. There you go. Final vector position. And we have this force here at the end. I'm making it as generic as possible. Okay. And I'll write that down here. The work done by the force F is X. That's the work done by the force F. Let's say the work done by force F is X. And now, you do the same thing, but through a different path. You do the same thing, but now through a different path, okay? So here we go. Instead, I'm gonna copy that. Copy and paste, good. And now, instead of using that upward path, I use a different downward path. Okay, here you go. And then I'm gonna eliminate this path here. It's the same force, but then I'm gonna call that the work prime because it's a different path done by the same force F, X prime, and let's say it's X prime. Okay. Okay, a force is going to be conservative, and I'm gonna write it down. If W prime F equal to WF, comma, then we say that then F is conservative. Okay, that's how we define a conservative force. Okay, let's see. Then F is conservative. That's the very definition of conservative force. And I'm going to give you an example. It's gonna take some time to do that, but okay. That's how we define. We don't have prime here. Okay. If this work here is equal to this other work here, which by the way, we drag the objects through a different path, then we say that the force is conservative. That's the very definition of conservative force. Okay. Otherwise, it's going to be a non-conservative force. Make sense? Right? That's the definition. I'm going to give you an example. Hopefully I have that ready elsewhere. Let me see here if I can find it. And P37 maybe. Let's see if I can. If I have it ready, I don't have to type from scratch. I wish I had an artificial intelligence to do all those drawings for me. And then he'll do, quality drawings, right? So let's see if it's here. It doesn't look like I have it here. Ay. Many of the drawings that I have here that you're seeing here, I have done and redone that over and over again. It must be here. Let's see if it's, no, it's not here. Oh no, it's not here. Okay, I give up. Let's do that from scratch, right? Example. I'm gonna give you an example of non-conservative force. Non-conservative force. So you can understand better what I mean about this path. Okay. Okay, so I'm gonna do the following. Erase. Instead of doing this convoluted path, I'm going to do a simpler path. Consider an object moving from point A, here's point A, to point B. Okay, here's point A. To point B. And send back, yeah. Point B to point C. That's one pass. To the front, okay? That's one pass. This object is moving from point A to point C. And let's see, I'm going to make it easier for you, okay? Here the distance is A. Oh, no. Here this distance is A, lowercase a. And here this distance is B, lowercase b. Pass one. Pass one. I'll do the non-conservative force first, and then I'll do an example of conservative force. We have 10 minutes to go. Okay. And then we have the second pass, a second different pass. Same object, but now it's moving from A to C through a different pass. Okay, through a different pass. A straightforward pass. And you already know that this distance is A and this distance is B, right? How am I gonna do that? Like that. Okay. A from here to here is A. Let's see. That's gonna be pass number 2. Okay, we're gonna do like that. Here you go. Okay, this is B. And this is A. This is A. I don't need that. And because this is a pass 2, right? A to C. 2 different paths, right? 2 legs and 1 single leg. Beginning and ending points are the same. From point A to point C in 2 different ways, taking 2 different paths. And the type of force that's acting in this object is going to be the force of friction. Okay? And then we gotta put one more vector here. Okay, and because it's the force of friction have to be at point A F sub K. Subscript, like that. See, this object is moving along this line, right? What about the other case? The other case, we have this same force of friction, but this force of friction, same I mean the same value, right? This force of friction has a different direction because we're taking a different path. It's going to have this direction along the vertical path, the y direction, and then we're going to have a different direction along the horizontal direction. The magnitude should be the same. Okay? The magnitude should be the same. Just by doing this simple example, you're going to see that the work done by the force of friction along this path is going to be different from the work done by the force of friction along this path. Okay? Let's do that. You know, calculate example of non-conservative force. Calculate the work done by the force of friction along 2 different paths. right? Having the starting with the same, with having different path, having the same starting and ending points. Okay? Fast one. Fast one. Let's go get it. Here you go. So here you go. From A, work done from A to C. That's how we do it. Okay, work done from A to C is going to be minus F sub K times A, right? Times A. Pass one, F sub K times A minus F sub K times B. Like that. Pass one. Make sense? The force of friction must be contrary to the direction of displacement, right? The object is moved from here to here, so the force of friction must be point down. The object is moving from here to here, so the force of friction along this path must be to the left. But now we have to do this one here. Let's take a look at pass two. Okay. Pass two. Pass two. From A to C, yes, it's from A to C. And what is going to be now the work done by the force of friction in this case? In this case, the work done by this force of friction is going to be this length times this F sub K, right? And this length is going to be what? The square root of B squared plus A squared, right? So it's going to be F sub K times square root of B squared plus A squared. And I'm going to like that. A to C. Note C, note C that, I want to call that even, prime. Note C that W prime A to C is different from W from A to C. Okay, it's different. Consequently, the force of friction is non-conservative. Okay? Let's see, 1157. I think I'm going to stop here because we have to do an example for example of conservative force, okay? We're going to do the example of a conservative force next time, and I'm going to tell you example of conservative force. Between parentheses, the weight is a conservative force. Right? The weight is a conservative force. The elastic force is also conservative force. There are very few conservative forces out there. Elastic force is also a conservative force. Okay? Most of the forces are non-conservative. And I'm going to do an example of the weight next time. Okay? Any questions? Let me save this in here. I'm going to stop my recording.